JMB, how are you all? I hope you all are good. I welcome you all to my YouTube channel. My name is Prince Rangbhara. I am a PhD scholar in the Department of Chemical Engineering at the Indian Institute of Technology, Ropar. So in today's lecture, we are going to discuss the deriving of the design equation of the plug flow reactor, right? So by utilizing the concept of the general mole balance equation, right? So let's get started. So in today's lecture, you will understand the important concept of the plug flow reactor, what is plug flow reactor, and how we derive the design equation of the plug flow reactor by using the general mole balance equation, right? So let's get started. So first of all, the question which arises in our mind is, what is plug flow reactor, right? The second question which arises in our mind is how the plug flow reactor differs from other industrial reactors, right? The third question which arises in our mind is what are the significant applications of plug flow reactor in the industrial uses, right? In the industrial applications, right? So you will get all your answers in these lectures, and you will understand. Okay, so let's get started. So first of all, the plug flow reactor. Okay, so we'll understand this diagram which represent the plug flow reactor, right? So let's say we'll understand the term the term plug flow and reactor, right? So let's say reactor. So reactor, which means the enclosed vessel. Okay, the reactor, which means the enclosed vessel in which the reaction will take place. It's called the reactor, right? The flow means, let's say the flow means the fluid is flowing through the entire reactor, right? It's called the flow means any fluid is flowing through the reactor volume. It's called the flow. Now plug which means let's say the plug flow reactor is also known as the tubular reactor, right? Tubular reactor, which means we have the tubular reactor, which means we'll have the hollow space inside the tube in which the fluid will flow through the volume of the reactor, right? So plug is a very technical fundamental term. Okay, so in order to understand the term plug, which means, let's say for example, if the fluid is flowing through the volume of this reactor, so the fluid which is flowing, right? So we'll understand at a very molecular level, right? At a very, so we'll try to zoom in, right? So we'll try to understand at a very molecular level. So let's say we will divide that fluid which is flowing to the reactor into a very small, infinitely small volume at a molecular level, right? So what will happen? So that fluid, so let's say for example this is the fluid, right, which is flowing through the reactor. Okay, so let's say this entire fluid we are dividing into a very small, infinitely small parts, right? So plug, which means a slice of fluid, right? Plug, which means a slice of fluid. Okay, so let's say this is the entire fluid which was flowing into the reactor. Now we are dividing that fluid into a very small slice. Okay, so this small slice of fluid is called the plug, right? Okay, so plug, which means small slice of fluid, which is a very thin slice of fluid which is flowing through the reactor. Okay, I hope you have understood. So other name of plug flow reactor is tubular reactor, right? So let's say we are having, so this diagram represent the plug flow reactor. So by understanding this diagram, we'll also understand like how we apply the general mole balance equation on the plug flow reactor. Okay, so let's say we have the plug flow reactor in which we have the inlet stream. Okay, so from by the inlet stream, the reactants will flow into the reactor, right? And now the reactants are present in the reaction environment where the reaction will takes place. Okay, and after completion of the reaction, the new products will get generated and which exit the reactor system through the outlet stream, which is indicated by Fj. Okay, inlet is indicated by Fj naught, initial molar flow rates and final molar flow rates, right? Okay, now let's say in order to understand the plug flow reactor, we need to in order to understand the plug flow reactor, we need to understand some certain assumptions, right? So let's say in order to understand the ideal plug flow reactor, we need to account certain assumptions, right? So first assumption is we are operating the ideal plug flow reactor at a steady state operation, right? So at a steady state operation, there will be no accumulation, right? So accumulation term will be equalized to 0. It's called the steady state operation, right? So there are no chemical species which is accumulating inside the reactor in the reactor volume, right? So for those reasons, the steady state operation, which means the accumulation term will be equalized to 0. Okay, so due to those reasons, the will operate the ideal plug flow at a steady state operation, right? The first assumption is clear. Okay, so the second assumption is in the ideal plug flow reactor, the fluid, the plug which is entering, okay, in the ideal plug flow reactor, the plug which is entering to the reactor, let's say the plug which is exiting to the reactor will not mix with the plug which is entering to the reactor. Okay, it's the second assumption. Okay, let me make very simplify to make you understand, which means the fluid which is flowing through the reactor volume, okay, which means let's say from the fluid which enters in from the inlet stream into the reactor. Now these are the plugs, right? So let's say we in the plug flow reactor we have the axis on the center, right? Axis of the reactor is on the center. Let's say for example, here we have the axis of the reactor, right? So this is the axis of the reactor, right? Okay, we have the axis of the reactor. Okay, so this is the axis of the reactor. Okay, and let's say, okay, now the second assumption is there will be no axial mixing with the fluid which is exiting the reactor and the fluid that is entering into the reactor, and there will be uniformly mixing of the all the fluid molecules in the radial direction. It's the second assumption in order to account for the ideal plug flow reactor. So we'll understand the second assumption in a very detail, right? So let's say axial direction, which means we have the plug flow reactor, and the axial direction, which means through the axis, right? So the dotted line, blue dotted line indicates the axial direction, right? So this is the axial direction of the reactor. Okay, so which means the fluid which is exiting the plug flow reactor will not mix with the fluid which is entering into the reactor. Okay, which means the plug this plug, okay, this entire thin slice of fluid will not mix with the adjacent fluid slice, right? So there is no axial mixing, right? So there is no axial mixing. Axial mixing is not present in the ideal plug flow reactor. Okay, which means let's say at this axial position, we'll have the radial mixing. Okay, so from axis to the top part of the reactor, from axis to the inner surface of the reactor, from here to here, it's called the radial direction. Okay, and from axis to the bottom inner surface of the reactor, from here to here, it's represent the radial direction, right? So there will be no axial mixing, but there will be uniformly mixing throughout the radial direction, throughout the cross sectional at the each and every axial position, right? So let's say at axial position of this, right, we are having this axial position. Let's say the first plug, the thin slice of fluid, and the second plug, the another thin slice of fluid. So there will be no mixing of the second plug with the first plug, or there will be no mixing with the mixing of second plug with the third plug, right? Or vice versa, there will be no mixing of the first plug with the fifth plug, right? Or likewise, there will be no mixing of the seventh plug with the fourth plug, right? So in the axial direction, there will be no mixing of the fluid which is exiting the reactor and the fluid which is entering into the reactor. I hope you have understood. Okay, but there are chances, but there will be uniformly mixing or in the radial direction, right? So there will be uniformly mixing in the radial direction, right? So from axial, so for example, which means these molecule can mix with the third molecule, or this molecule can mix with these molecules, or this molecule can mix with this molecule, or this molecule can even mix with this, and vice versa. all molecules can with all molecules can mix with each other. Okay, so there will be radial mixing, okay, in the idealized plug flow reactor. So due to the radial uniformly mixing, due to which at this axial position, okay, at this axial position, will have the uniformly mixing in the radial direction, due to which the concentration, the temperature and the reaction rate will remain constant with this axial position. Okay, I hope you have understood. Which means at this axial position we'll have the uniform mixing. Due to uniform mixing, we have the constant rate of the reaction, we have the constant concentration, uniform concentration throughout the radial direction, and we have the uniform temperature. Okay, so likewise, we'll for each and individual axial position with respect to time, we have the uniform mixing in the radial direction, due to which we have the uniform concentration, temperature, we have the uniform concentration, temperature and rate of the reaction with respect to each and individual axial position, right? I hope you have understood the second assumption. Okay, the first assumption was the ideal plug flow reactor will be operated at a steady state where acclimation term is equal to 0. The second assumption is the fluid which is exiting the plug flow reactor will not mix with the fluid which is entering into the plug flow reactor, right? So there will be no axial mixing. Okay, so there will be no axial mixing, but there will be uniformly mixing in the radial direction. Okay, in the radial direction. Okay, due to which the concentration, temperature and the rate of the reaction will be uniform throughout the entire cross section with respect to each and individual axial position, right? I hope you have understood. Okay, now the third assumption is the flow should be uniform throughout the entire reactor volume, right? The flow of fluid which is flowing, the flow of fluid which is flowing, the flow of fluid which is flowing throughout the entire length and volume of the reactor should be uniform, right? It's the idealized plug flow reactor. Okay, I hope you have understood. Okay, now let's say by accounting all these assumptions, and by utilizing the general mole balance equation, the concept of general mole balance equation, we'll try to derive the design equation of plug flow reactor, right? Okay, so I hope you have understood, right? So let's say we have the general mole balance equation as in minus out plus generation is equal to accumulation, right? So inlet is represented by initial molar flow rate, which is Fj naught, minus outlet is represented by Fj, plus generation is indicated by Gj is equal to accumulation term can be indicated by dnj by dt, right? So we can write in this form. Okay, so we are writing the generalized mole balance equation. Okay, so let's say now let's say we are very clear, right? The steady state operation, we are accounting the steady state operation, which means the accumulation term is equal to 0, due to which the dnj by dt will be equalized to 0, and the generation term can be represented as delta g, the change, the rate of generation, okay, can be understood by the integration of rg into dv into delta v volume. Okay, now let's say what we are doing, why we are writing delta v here. Okay, we'll understand that. Let's say in order to account the entire reactor behavior, so what we are doing, we are delving more deeper into the molecular level. Okay, so in the molecular level where we are accounting a very finite volume, okay, finite volume delta v. Let's say for example let's say we are accounting for this finite volume delta V, right? This is a very finite volume delta V, right? So let's say delta V volume, and in this delta V volume we have the rate in this delta V volume, what will be the rate of generation, okay, what will be the rate of formation, okay. So in this finite delta V volume we'll have the delta G, right, the rate of generation of any species G with respect to the finite volume delta V, right. Okay, so due to those reasons, I already explained in the previous lectures, right? If you want to recall, I request you to please watch my previous lecture, okay? Why we are writing the delta Gj is equal to integration of Rj into dV, and we are trying to convert into the simple form Rj into delta V, right? So for the finite volume of delta V, for the finite volume of delta V, will have the uniform rate of generation throughout the entire finite volume of delta V, and we'll have the uniform rate of formation of any chemical species throughout the entire delta volume V, right. So due to those reasons we are writing this form into this form of generation term. I hope you understood, right. So delta Gj can be written as Rj into delta V, because in the delta V volume, in the finite delta V volume, we will have the uniform rate of formation and we'll have uniform rate of generation, right. So due to those reasons, we'll apply these values into the general mole balance equation, right. So let's say we'll write the inlet term Fj, okay. So inlet term minus outlet plus generation is equal to 0. So we'll understand this equation 4, okay. So let's say here we will have the volume as V equal to 0, right. V equal to 0 means initial volume, right. Initial volume V equal to 0, right. And after here we'll have some certain volume, right. From here to here we'll have some certain volume, so we'll define as here certain volume V, okay. Here, because we are taking this finite volume into analysis, right, into the part of our interest is the finite volume delta V. By understanding the what is happening into the delta V, we will try to account, and we'll try to account the entire reactor volume, okay. So here let's say at this position we have the volume V, and after here at this position we'll have volume, like we'll have volume of V, we'll have the volume of V plus delta V, right. V plus this delta V volume will be here, right. Okay, so for the inlet part, the flow rate which is entering to the volume at position V will be indicated by Fj at volume V, position V, and the outlet flow rate will be indicated by Fj at the position of V plus delta V. Okay, so in finite volume delta V, we will have the uniform rate of generation which is delta Gj, right. So we are accounting into that, okay. So inlet can be written as the, in this very finite infinitely small delta V volume we'll have the uniform flows, right, flow rate, right, uniform flow rate, uniform rate of generation, uniform rate of formation, due to which the molar flow rate Fj at position V is the inlet minus molar flow rate Fj at the position of V plus delta V is the outlet flow rate, okay. From here is the inlet and here is the outlet, right. So we are writing inlet as Fj at position V minus Fj at position of V plus delta V plus the generation term and is equal to the acclimation term, right. I hope you have understood. Now we are trying to rearrange the equation 4, and we are trying to make the subject as Rj into delta V, okay. So due to which we are transferring the Rj into delta V on the right hand side, so the sign will change, okay. So due to those reasons we can write as Fj at the position of V minus Fj at position of V plus delta V is equal to minus of Rj into delta V, because we have shifted this term into on the right hand side, due to which the sign convention will change. Now we are multiplying this negative sign we are shifting the negative sign on the left hand side, due to which here we have positive, so minus will multiply here, so minus of fj at delta v, and here we already have minus, so again minus will multiply, so minus minus is plus. So the second term, outlet term, will become positive and the inlet term will become negative, right? And we are making the subject as rate of generation of any species, rate of formation of any species j. So rj is equal to v positive of fj at position of v plus delta v minus of fj at delta minus of fj at position v, and we are dividing the delta v on the left hand side, right? So divided by delta v. Okay, so here we have obtained the equation fifth, okay, which represent the difference quotient. Okay, now both the term means different quotient, will understand that. Okay, so different quotient, which means the average rate of change of molar average rate of change of molar flow rates with respect to the finite volume delta v, right? The rate at which the molar flow rate will change with respect to the delta v, it's understood by the term difference quotient, right? Now let's say but the reaction rate and the flow can vary along the length and volume of the reactor. Okay, now see, but the reaction rate and flow can vary along the reactor length of the reactor and volume of the reactor as the conversion changes, right? So by understanding this sentence, or two questions which arise in your mind is like how the flow will change in the plug flow reactor, right? And how the flow will change along the length and volume of the reactor. And the flow should not remain constant throughout the entire reactor, volume and length of the reactor, right? So these are the two questions which arise in our mind. So in order to understand, I will answer to that questions, right? So let's say how the rate of reaction and flow will vary along the length of the reactor. Okay, in the first assumption I told, like flow should remain constant throughout the entire length of the reactor and throughout the entire reactor volume in the first assumption of the idealized plug flow reactor, right? So now in this sentence I have written like rate of the reaction and flow can vary along the length of the reactor as the conversion changes. So how? We'll understand that. So let's say here the flow represent the two flows. Okay, first flow is volumetric flow rate and second is the molar flow rate of species of reactants, product, byproducts, intermediates, or any chemical species, right? So let's say we have two flows. First is volumetric flow rate, so we'll understand the volumetric flow rate, right? So volumetric flow rate, which means let's say units are liter per second, liter per minute. For example, 10 liters per minute of fluid is flowing through the entire length and volume of the reactor, right? So 10 liters, so at first minute the 10 liters of fluid which is flowing through the reactor, right? And another second minute, another 10 liters of fluid which is flowing through the reactor, right? So volumetric flow rates, okay, it's called the volumetric flow rates, right? 10 liters per minute of fluid which is passing through the reactor. Okay, so let's say in volumetric flow rates also we have the two case. Let's say first of all, if the reaction this is the reaction environment. Okay, so in the reaction environment, let's say we are practicing the vapor phase reaction, right? So we are taking the vapor phase reaction or the liquid phase reaction. Okay, so what if we are having the liquid phase reaction, and what if we are having the vapor phase reaction, right? Then we need to account both the cases to understand the volumetric flow rates, right? So in volumetric flow rates, let's say first case is if we are having the liquid phase reaction which is taking place inside the reactor volume in the reaction environment. Okay, if we are having the liquid phase reaction, and in the liquid phase reaction, if we are having the liquid phase reaction which are not compressible, right? Incompressible fluids, right? So what does the term means incompressible? So incompressible, which means the fluid, those fluid whose density doesn't change with the progress of the time, with the progress of the reactor are called the incompressible fluids. Okay, for your example, the incompressible fluids like water, vegetable oils, or any engine oils, right, are the incompressible fluids, which means those fluids density will remain constant throughout the reactor, throughout the volume of the reactor entire. Those density will not change. Okay, by applying the pressure or temperature, the density will remain same. Okay, I hope you have understood. It's are called the incompressible fluids. And okay, so let's say water. So water we cannot compress by applying the pressure and temperature, right? Up to significant pressure and temperature, if we are applying to the water, then we cannot compress the water, are called the incompressible fluids, right? So let's say we are having the liquid phase reaction and the incompressible fluids. So in which during the progress of the reaction, during the with respect to time, with the progress of the reaction, with respect to length and volume of the reactor, the density of liquid will remain same. Okay, due to those reasons, the volumetric flow rate will also remain same. Okay, so in liquid phase reaction, the incompressible fluids will have uniform volumetric flow rate. We will have constant volumetric flow rate. Okay, we'll have constant volumetric flow rate. Now let's say we have the second case. Let's say if we are having the gaseous phase reaction, right? So let's say in the reaction medium, the gaseous phase reaction is taking place, right? So now what will happen? So all the gaseous phase reaction or all the gases are compressible. Okay, now here the word term compressible means the compressible, which means all the gases can compress. Compressible, which means the density of fluid will change by applying significant amount of pressure and temperature. The density of the fluid, the density of the gas will change. Okay, during the progress of the reaction and progress of the time, are called the compressible fluids, right? So due to those reasons, the volumetric flow rate will not remain constant throughout the length and volume of the reactor. Okay, and if we are having the gaseous phase reaction, compressible fluids, the density will change. Okay, due to those reasons, the volumetric flow rates of gaseous phase reaction will not remain constant, okay, throughout the length and volume of the reactor. Okay, and let's say if in the reaction, in the gaseous phase reaction, the number of moles will change, the density of the fluid gaseous phase system will change, due to which the volumetric flow rate will not remain constant with the length and volume of the reactor. I hope you have understood, right? So here we have completed the first part of volumetric flow, right? Now let's say we have the another flow, which is the molar flow. Okay, molar flow rates of species of reactant, intermediates, product, byproducts, and etc. Right? So let's say in order to make you very simple, we'll take two. Let's say first is reactant and product. So we'll take two molar flow rates only. Okay. So let's say with the progress of the reaction, now what will happen? The moles of reactants will get consumed, right? So let's say we have the reactants, right, which is flowing through the entire length and volume of the reactor, right? So these are the reactants. Let's say now with the progress of the time, with the progress of the reaction, the moles of reactants will get consumed, will disappear from the reaction environment, and will get converted into the new products, right? So moles of reactants will get consumed, will convert into the new products, okay, with respect to the progress of the time. And likewise with the progress of the reaction, with the progress of the times, will obtain the reactants will get consumed and new products will get formed. Okay, so due to those reasons, the molar flow rate of reactants will decrease along the length and volume of the reactor, right? And the molar flow rates of product will increase along the length and volume of the reactor. How molar flow rates of product will increase? Because during the progress of the reaction, during the progress of the time, the new products will generate more, because more reactants are getting consumed, they are converted into the new products, okay, during the progress of the reaction. So due to those reasons, during the progress of the time, during the progress of the reaction, the molar flow rates of reactant will decrease along the length and volume of the reactor, and the molar flow rates of product will increase along the length and progress of the reaction, right? I hope you understood. Now the rate of reaction of reactants and products. So rate of reaction of reactants will be less than 0, and the rate of reaction of product will be greater than 0. Okay, I have already explained why we are writing Ra less than 0 and Rb greater than 0 in the previous lectures, right? If you want to recall, I request you to please watch my previous lectures, right? And the total molar flow rates, let's say the total molar flow rate means the total moles of reactants and products will remain same, constant, or may consume throughout the entire reaction during the with the progress of the reaction and with the progress of the time, along with the length and volume of the reactor. I hope you have understood, right? So I hope you have understood what does the term means flow. So we have the one volumetric flow rate and one molar flow rates, right? So molar flow rates will change. Okay, molar flow rates of species of reactants and product will change with respect to the length and volume of the reactor. Okay, I hope you have understood. So now let's come back here, right? So the reaction rates and flow can vary around the reactor. I hope you understood now what I was trying to explain you, right? Now let's say how the flow part we have understood, right? Now how the rate of reaction will can vary along the length of the reactor. I already explained, so I will again explain in very brief. Let's say reaction rate. So at each and individual axial position, so let's say axial position 1, 2, 3, 4, 5, 6, 7, and 8. So we have 8 axial position, right? So now at this axial position, let's say we are so as per the uh, assumption for the ideal plug flow reactor, we will not have axial mixing. Okay, in order to understand the ideal plug flow reactor, there will be no axial mixing, right? So with respect, there will be no axial mixing, right? But there will be radial mixing, which means all these molecules can mix with each other in the radial cross sectional with respect to the each and individual axial position, right? So this axial position of one will have the uniform mixing in the cross sectional of plug flow reactor. In the cross section will have the uniform mixing. Due to the uniform mixing, we'll have the uniform concentration throughout the radial direction, due to which at each and every axial position will have the uniform concentration, uniform temperature, uniform rate of reaction with respect to each and individual axial position, right? Because as per the assumption, we'll have the uniformly mixing in the radial direction, due to which, due to the uniform mixing in the radial direction, at each and every axial position will have the uniform concentration, temperature, and rate of the reaction, right? Along the entire along the entire length and volume of the reactor, which means here at this axial position we'll have rate of reaction as R1, but if the axial position change, then rate of reaction will change. So at axial position 2 we'll have another rate of generation, another rate of formation, right? Why? Because see, so there will be no mixing of any molecules with each other, right? For example, this molecule will not mix with this molecule, these molecules will not mix with any of the other molecules, right? Same way, these molecules will not mix with these molecules, or these molecules will not mix with these molecules. This molecule cannot mix with these molecules, or this molecule will not mix with these molecules, right? As per the assumption, because there will be no axial mixing. Axial mixing will not take place, right? Okay, so due to those reasons, at each and individual axial position, so let's say at this position, we'll have uniform rate of formation, which is R1. At this position, this cross section in the radial direction will have uniform mixing, uniform concentration, temperature, and reaction rate. Okay, so here we have reaction rate of R2. At this position we have the uniform reaction rate of R3. Likewise R4, I5, I6, I7, R8, right? Which means the rate of reaction will change along the length and volume of the reactor, but for the particular axial position and for the particular cross sectional of reactor will have the uniform reaction rate. I hope you understood. Okay, it's quite tricky, so please understand. Okay, I hope you have understood. So due to the, with respect to the length and volume of the reactor, the concentration will vary along the axial direction. The rate of the reaction will vary along the axial direction. okay, due to which the reactants will get consumed, new products will get generated, due to which the rate of the reaction will vary. Okay, so in order to have the exact analysis like what is happening, okay, in order to understand in a very detailed manner, we need to account the instantaneous rate, right, at a very single point. Okay, so in order to understand instantaneous rate at a very single point, which means we'll try to apply the limit delta v tends to 0 into the equation 5, right? So what does this term means, limit delta v tends to 0? Let me make you understand in very simple. For example, if we are having the reactor volume of 10 liters, right? So let's say we have the reactor volume as 10 liters, right? So entire reactor volume is 10 liter. Now if we divide the 10 liter into a 10 parts, okay, so each and individual part will have 1 liter volume. So 1 liter to second another 1 liter, 1 liter, likewise 10 times, right? So we have divided entire reactor volume into the 10 individual parts, okay, 10 individual parts. Okay, so each part will represent 1 liter. If we sum up all the parts, then we'll have the total volume as 10 liters, right? I hope you have understood. Now why we are applying the limits of delta v tends to 0, I will make you understand in very simple. For example, in order to account the exact analysis like what is happening in the reactor, in order to understand that, and in order to derive the rate design equation of the Plug Flow Reactor, what we'll do, we'll try to divide the entire reactor volume into a very small, infinitely small parts. Okay, for example, the entire volume of 10, same example I will take. If we are having the entire reactor volume has 10 liter, now we are trying to divide into very small, infinitely small parts, right? So let's say 10 divided by, we are dividing the 10 liters, entire reactor volume 10 liter into 1 lakh parts. Okay, 1 lakh parts we are dividing. So 10 divided by 1 lakh if we do, then what answer will get? 0.0001, right? 0.0001, right? Which means the delta v, very small delta v, thin volume, tends to 0.0001, right? 0.0001, which means the delta v tends to 0. I hope you have understood, right? So for those reasons, we are applying the limit of delta v tends to 0 to the equation 5, right, in order to convert from the finite difference form. So this equation 5 represent the finite difference form, right? Finite difference form. Why finite? Because we are accounting for the delta v volume, right? So we are trying to switch from the finite difference form to the differential form, which means, so in order, so differential form, right? So differential form represented as, so we can write the entire equation 5 to equation 6, right? So Rj is equal to the dfj, the change in molar flow rates with respect to the very infinitely small volume delta v. Okay, so we have divided the entire reactor volume into 1 lakh parts, right? 1 lakh infinitely small parts. Okay, so we have tried to convert the finite difference form into the differential form, which represent the Rj, the rate of generation of any, rate of formation of any chemical species J. Okay, is defined as the rate at which the molar flow rates of chemical species J changes with respect to the infinitely small volume, the dV, right? So the equation 6 is the generalized form. Now we can write the equation 6 in the form of reactants, right? So we'll write the rate of formation of chemical species J in terms of reactants. So we'll apply minus Ra, right? Because the rate at which the reactants will disappear is indicated by minus Ra. So minus Ra is equal to DFJ represent the any chemical species, but here we are specifying for reactants. So DFA, we'll write A is a reactant. So minus Ra is equal to DFA by dV. I hope you have understood, right? So now we can convert this equation into the dV form, right? So we'll make the subject as dV. So dV is equal to dFA upon minus Ra, right? Now is the equation 7. So in equation 8, we'll try to apply the integration on the both sides of the equation, right? We'll try to apply the integration on the both sides of the equation. So why we are applying integration? in order to count all the infinitely small parts. Okay, so we are applying the integration. So we'll add up all the very infinitely small parts. Okay, so we'll have the overall reactor behavior. We'll analyze the overall reactor behavior. Okay, I hope you have understood. So due to those reasons, we are applying the integration on the both the sides. Okay, so integration of dV from limits 0 to V. So from initial volume V is equal to 0 to entire volume V. Entire volume V. Okay, entire volume V. Right? From limits from V is equal to 0 to entire volume V, from initial to the final volume V. Okay, from 0 to final volume V is equal to from integration of dFA upon minus RA from FA0 to FA, from initial molar flow rate of reactants FA0 to the final molar flow rate of FA, right? I hope you have understood. So here we have the equation. Now if we integrate this, so what we'll get? Integration of dV will have the remaining only V. Okay, from limits final to initial. Final minus initial is V minus 0. So will remain with only V. So V is equal to integration of FA0 to FA dFA upon minus RA is the equation 9, right? So equation 9 represent the design equation of plug flow reactor. I hope you have understood how we have derived the design equation of the plug flow reactor, right? So by utilizing the design equation of plug flow reactor, we can analyze the volume required in order to achieve the desired conversion with respect to the reactor, right? I hope you understood the design equation of the plug flow reactors. Now let's say we'll understand the figure. Okay, so here the figure represents the profile of molar flow rates in a plug flow reactor, right? The profile of molar flow rates of reactant Fa and molar flow rates of product FB, right? So here the volume is let's say we have the entire reactor volume from V is equal to V is equal to from 0 to V is equal to V, right? So with respect to the length and volume of along the length and volume of the reactor, the molar flow rates of reactant will decrease. Okay, why the molar flow rates of reactant will decrease? I already explained, due to the due to the progress of the reaction. Okay, with the progress of the time, the reactants will get consumed and will get converted into the new products with the progress of the reaction. Okay, and final product will be formed. So during the progress of the reaction, the reactants will get consumed, the reactants will get disappear and will get converted into the new products. Okay, due to those reasons, the molar flow rate will decrease slowly and gradually. The moles of reactants will get consumed, due to which slowly and gradually it will decrease. Okay, and same way, this plot indicates the molar flow rates of product with respect to the length and volume of the reactor. During the progress of the reaction, new products will get generated, right? So let's say at the initial time d is equal to 0 and b is equal to v naught, we have 0 products, right? Product was not formed due to reaction doesn't start, right? So with the progress of the time, with the progress of the reaction, okay, and with the progress of the length and volume of the reactor, the new products will form due to the reaction of reactants, right? And new products will get generated. So during the progress of the reaction, during the progress of the reaction, during the progress of the time, and during the length and volume of along the length and volume of the reactor, the new products will form. Okay, so due to which we have the nature of the plot in increasing, right? So new products will get generated. I hope you have understood, right? So let's say here, this from here to here, this part where we have the steepest slope, right? Steepest slope. So this steepest slope, from here to here we have the steepest slope, right? And same way from here to here we have the steepest slope, right? Steepest slope. So this steepest slope in the reactant molar flow rates and in the product molar flow rate, which indicates, like, let's say in the progress of the reaction, in the initial volume, in the initial length and the volume of the reactor will have the higher concentration of the reaction in the initial length of the reactor. So due to the higher concentration of the reactants will have the higher rates of the reaction, right? So due to the higher reaction concentration, we will have the higher reaction rate in the initial time period, due to which the rate of reaction will be very high. Okay, the molar flow rates will the molar flow rates of reactant will drastically reduce, right? Will drastically consume, and due to which it reduced drastically. So we are having the steepest law, and due to the drastic change of the consumption of the reactants, new products will generate very fast. Due to which we have the steepest law. So as fast the reactants will get consumed, the new products will generate. Okay, so and I hope this understood, right? These both parts. And in this part we have the flatter curve. In this part we have the flatter curve, which means after here we have only small amount of reactants which is present in the reaction environment, and due to which we have the lower concentration of the reactants, due to which the rates of the reaction will decrease, and rate of the formation of product will also decrease. Okay, due to which the curve flattens, and after that all the reactants are consumed, due to which there are no more reactants left in the reaction environment to carry out the reaction. Okay, if we are not having any reactants present in the reaction environment, so there are no products which can generate during the progress of the reaction, right? So reaction comes to completion, so due to which the curve flattens. Okay, here there are no reactants left, all the reactants are utilized and converted into the new products, so due to which the curve flattens. Okay, I hope you have understood. So in today's lecture, we have understood in detail in very important significant concepts of the plug flow reactor, right? And we have also understand how we derive the design equation of the plug flow reactor by utilizing the concept of the general mole balance equation, right? I hope you have understood, right? And I request you to please make all the notes, right? And if you have any question, then please feel to comment below. I will try to reply to each and every comments, right? So until then, stay focused, keep learning, and stay curious. Thank you for watching my video. JMB.